So good afternoon, everybody, and thank you for joining us for our Australasian Fluid Mechanics Seminar of the Day, presented by Assistant Professor Ricardo Vinuesa from KTH. Before I get started, I just want to give a shout out to my fellow Victorians. It's a pretty brutal lockdown that we're in at the moment, and I hope that you're able to try and stay in contact with as many of your family and friends as possible, because I've found that that's been probably the most helpful thing to try and not go completely crazy. But I'd like to introduce today's speaker. So Dr. Vinuesa did his undergrad in Valencia in Spain, and then he did his PhD at the Illinois Institute of Technology with Hassan Naguib. And for those of you who were at our marathon seminar week in February, Professor Naguib actually gave a talk and mentioned some of the things that Ricardo had worked on when he was there. After his PhD, he did a short stint at Airbus in Madrid, and then he was a postdoc at KTH, and he's been an assistant professor there since 2017. And in addition to being a professor there, he has also won the Göran Gustafsson Award in Sweden. And today he's going to be talking to us about wall-bounded turbulence, in particular machine learning. This was the topic that I actually met his student who was working on this at the Madrid Summer School last year. And thank you very much for agreeing to give a seminar for us today.
Thank you very much for the kind introduction and for giving me the opportunity to present today. I'm going to talk about predictions in wall-bounded turbulence through recurrent and convolutional neural networks. And this work has been developed in the context of the Flow Group at KTH and the Swedish eScience Research Center in Stockholm, in Sweden. So I would like to start by acknowledging my many collaborators in this work, in particular Luca Guastoni, who is a PhD student in our group, who has done a big part of the work that I will be presenting today. We have also collaborations with the machine learning group at KTH, with University of Tehran, and also with collaborators in Carlos III University in Madrid. So this is a collaborative effort, and I will be highlighting some of the most interesting results to discuss. So the motivation for this work comes from the numerous success stories from machine learning in a wide range of areas. So it's quite prominent, the ImageNet challenge about image classification, where now neural networks have errors of 2% and humans have 5% errors. So we actually make more errors when classifying images than neural networks. Predictive text, finance, there are many applications where machine learning is really helping a lot. I like this example of one of the first cases where a machine was competing against a human in a task. That's when the IBM Deep Blue supercomputer defeated the world champion of chess, Garry Kasparov, 1997. So you can see here how it was really a big accomplishment at the time, and the media captured the importance of the moment. But it turns out that it's reasonably easy for a machine to play chess, because chess is a game that doesn't have so many options in the end. So with some sort of brute force computing, the machine, Deep Blue, could evaluate a subset of the possible moves and then select the most adequate ones, and without so much of a sophisticated approach, could defeat Kasparov. Turns out that there are other games like Go, which has got recently very popular thanks to DeepMind, which are significantly much more complicated than chess. So Go, if one looks at the possible number of moves in a turn, it has many more possible moves, and the typical amount of turns that a game takes is also much longer. So one can define the complexity of a game by looking at the number of moves raised to the power of the turns. And then you can see that the game of Go is significantly much more complex than the game of chess. So one cannot just evaluate a number of possibilities and see the most adequate ones. If one wants to play Go, one needs some sort of a strategic thinking, or some sort of intuition of what is the best way to play, essentially. So this is why this game has captured the attention of DeepMind, and they have been working on developing different ways of playing Go. So they started with this algorithm called AlphaGo, where what they did is that they were showing the games of the best human players to this neural network-based algorithm, and then essentially it learned from them, and it became extremely good at playing Go, up to the point that it was able to defeat Lee Sedol, who is the world champion of Go, by 4-1. So it really was able to defeat the best human in a game that is actually much more complicated than chess. And then the next level is what they did in this algorithm AlphaGo 0, where they removed any human knowledge from the table. So essentially they gave this neural network-based algorithm just the games, the rules of the game of Go, and it allowed to play it against itself. So it self-improved through playing, just knowing the rules of the game through reinforcement learning. And what is interesting is that here in this figure, you can see the performance of this network as a function of the training time. And what you can see, this horizontal line is the performance of the previous AlphaGo algorithm. And in less than 2 days, you can see that AlphaGo 0 reached superhuman performance. So in less than 2 days of training, this algorithm based on knowledge that it had developed itself, so no human input at all, it was able to achieve superhuman performance. So that was quite an accomplishment as well. And we have also looked at a wider range of applications where machine learning or AI, which I will use indistinguishably in this talk, can help. We have a recent review in Nature Communications, which you can see here if you want more details. We basically looked at the 17 Sustainable Development Goals from the United Nations, and we look for published evidence on how could AI impact positively or negative each of these goals, which are split also into 169 targets. So basically going from sustainable cities to climate change or no poverty, all these targets of sustainability for the 2030 agenda. What we found in this review, and you can see all the details there, is that 79% of the targets could be positively affected by AI, and only 35% could be negatively affected. So in principle, there is a quite positive impact of AI on a wide range of applications. Of course, one needs to be careful also with the negative ones, but it seems that there are many areas where AI can really help. And now going maybe to our topic today, so machine learning applied to fluid mechanics. There are also many areas where the feasibility and the potential of AI has been assessed in fluid mechanics, starting with a seminal paper of Milano and Komosakos, who used neural networks to model the near-world region of turbulent channels. So this was almost 20 years ago. And then more recently, there has been kind of like an exponential increase of machine learning papers looking at fluid mechanics applications. Beck and others have developed subgrid scale models for LES. Jimenez has looked at the identification of structures into the decaying turbulence. Fukami and others, the group of Koji Fukagata, they have been looking at development of inflow conditions and super resolution applications using machine learning. Dweisami and others have highlighted the potential for RANS modeling, and Branton and others, the potential for basically for flow control and dynamical systems approaches to fluid mechanics. So there are many areas where within fluid mechanics where machine learning can help, and that's what motivated us to look at what could be done in the context of turbulence. So we looked at two main sections. I'm going to split today's talk into two parts. First, we're going to focus on temporal predictions, so how to advance the flow in time using neural networks. And for that we will use mostly recurrent neural networks. In the second part, I will talk about spatial predictions, so basically non-intrusive sensing, and for that I will talk about convolutional neural networks. So let me start with the first part. This is about temporal predictions, and to do that we start with a simple model of the near-world cycle of turbulence. This is a model developed by Moehlis and others, which is basically, it's basically 9 spatial modes, which are described here, that are combined to build the instantaneous flow field. And the point is that we need to be able to predict and understand the evolution of the temporal coefficients of these spatial modes. As you can see here, this is a sinusoidally forced flow, so you get the laminar profile is a sine function. and then the different modes represent the streaks, the Streamwise vortices, their instabilities and coupling. What we do is that we, because this is a very cheap model, this is a system of ODEs, so you can produce a lot of data for training and testing and validating. So we produce over 10,000 data sets of 4,000 time units each, using the approach described by Kim. So we perturb the fourth coefficient in order to vary the initial condition and produce a sufficiently complete set of conditions. And we only consider data sets that were fully turbulent in the whole range. So we don't look at relaminization, we just focus on the turbulence. And this is an idea of how the flow looks like. All the details of this study are found in this work by Streamwise and others. This was in Physical Review of Fluids last year, so everything can be checked in more detail here. What I'm showing is a sample evolution of the 9 temporal coefficients. What you can see is that at some point in this series, the flow relaminarizes. That means that A1 goes to 1 and the other coefficients go to 0. We would not consider this series for the training. We would only consider a series that is fully turbulent. But what you can see in the turbulent region is that the flow looks like it has the elements of the near wall cycle. So you have the Streamwise vortices, the streaks, you have the span-wise variation of those streaks. So in principle, this is a model that can help us to reproduce some of the behavior that you have in the near wall cycle of turbulence. And to perform the predictions, we start with the easiest type of neural network. This is the so-called multi-layer perceptron, the NLP, which is a neural network that is fully connected in all the layers. And the interesting thing of this network is that it does only point predictions. It does not take into account any temporal dynamics in the data, and is the baseline performance, basically. So when one is looking at machine learning models, the MLP is the basic level of performance that one can achieve, and then any modifications on top of that gives you the level of improvement that one can get, essentially. So this is how an MLP looks like. On the left, you have the input vector. So this is the data that you use to perform the predictions. In the middle, you have L hidden layers, which basically contain the coefficients to perform the predictions that we want to do. And the output vector is here on the right, which in our case has dimension M equal to 9, because we're predicting 9 coefficients. The dimension of the input depends on how many steps we take for the predictions. So if we take P previous steps, then the dimension of the input will be 9P, and 9 coefficients multiplied by the number of steps. So usually this input vector will be much larger than the output. And if now we zoom in a little bit into these neurons to see what's inside, what we see is that in the end, this is just a matrix vector multiplication plus some non-linearity. So this matrix vector multiplication, the array that resulted in this layer here is just the result of multiplying all the weights, which is a matrix, multiplied by the input plus the biases. So it all boils down to fitting or to adjusting the values of the weight matrices and the biases. So these are the coefficients, the free parameters that are being learned, are being adjusted during the training process through the backpropagation algorithm. And if we left it there, just with a matrix vector multiplication, this would be linear algebra, and there would be not so much of a, I mean, what is the big deal then, right? The point is that we introduce non-linearity through this activation function. So we, after performing the matrix vector multiplication and adding the bias, then we introduce a nonlinear operation, which is what allows neural networks to be able to predict a very wide range of signals of very complex nature. And this activation function in the end is just a filter of the output. It's quite common to use a sigmoid or a hyperbolic tangent. Here we show a sigmoid, and the idea is that through this nonlinearity, one can exploit the gradients that allow us to learn and to basically adjust and fit those parameters. No? That's what training is about. So a little bit about training. Typically what we do is that we split the training data set, so we get 80% for training and 20% for validation. What is training and what is validation? This in this left figure, what I'm showing is the loss. The loss would be the error function, basically. So how far you are from the predictions that you're trying to make, and then on the horizontal axis, the number of epochs. So how many times you're going through the batches of data to train. And the blue line is the training loss, which means how well are you predicting the data that you have seen during the training. And of course, this blue line goes down because the more you train, the better you are able to predict data that you have seen. But the red line is what is called the validation loss. That's how well you are predicting data that you have not seen during the training. And typically this is going to be larger because of course you're not going to fit so well the data that you have not seen, but if everything goes well, this should be decreasing as well, because you're also, the more you train, the better you're able to generalize the training information. What can happen? Well, what could happen is that the training loss goes down, but the validation loss goes up at some point. This is what is called overfitting, and that really means that you are fitting too well the data that you are given, but you're not able to generalize. And that means that you need more training data so that the network can see a wider variety of cases so it can generalize better. Another possible problem when training is what is called the underfitting. And the underfitting is observed when the validation loss is not really going down. And that means that the capacity of the network is not enough. So that means that you basically need more parameters to fit the data that you're having. This part of the work was done in TensorFlow with the front-end Keras. So it's all open source. And on all the, by the way, all the codes and all the libraries that we're using in this work, they're fully available in GitHub as well. So if you go to this paper and you want to play with the data, you want to train, you want to perform predictions, everything is there. And we're also happy to discuss if you have any questions. So this very first prediction performed with the MLP gives us an idea of, well, how much does one need to actually get results, right? We performed, we consider a network with 3 hidden layers and 90 neurons per layer. And we keep in mind that the MLP, as I mentioned at the beginning, it does point predictions. So it does not know how the data is organized in time. So we're using P equals 500 previous steps to perform the prediction of one single step. And because I have 9 coefficients, I'm using 4,500 data points to only predict 9. And this is because this network does not know how the data is organized in time. It just knows that you have many points to predict the next one. So that gives us an idea of how this doesn't seem very efficient, right? I mean, you should incorporate the information of the time dynamics, and that will come later. But even like this, without knowing about the temporal dynamics, the instantaneous flow field looks more or less like what you get in the reference. I mean, it seems that the span-wise movement of the streaks is perhaps not as close as what you had in the reference, but the flow kind of looks a bit like what it should. If one looks at the turbulence statistics, so the mean velocity profile, the fluctuations, and the Reynolds shear stress, then what you have is that you find quite good agreement with the mean, but you see significant deviations in the Reynolds shear stress. So you get 36% error in the fluctuations and in the shear stress. So clearly there is room for improvement in this type of prediction. And what we did was to play a little bit with the architecture of the network. So we consider a much bigger network here. We look at the 5 hidden layers and also 90 neurons per layer. And we can see that we can improve. This would be the error in the mean, and this would be the error in the fluctuations. We can improve the error in the mean. We still have quite large errors in the fluctuations, so 20% error in the fluctuations. So this gives us an idea of how far one can go with MLPs. I mean, we can get decent predictions, but still we're quite far from getting a very good agreement with the reference. The next level of sophistication would be what is called the recurrent neural network, right? So this is a network that essentially incorporates the temporal dependencies in the input data, and therefore that allows us to understand a little bit how the data is organized. So this is a schematic representation of an RNN, of a recurrent neural network. This is all described in the proceedings paper by Guastoni and others. And what you see on the bottom is the input vector. So here is the input data that we're having. And here on the top, I'm having the output of this current step. And you can see that because of how the data is organized, you can already see that the temporal dependencies are taken care of or are accounted for. How are they accounted for? The key is what you see here. There is a recurring connection in this particular place, which basically gives us the information of how the temporal dynamics are being accounted for. So if we look at this particular neuron over here, we see from the bottom, we get the input of the current step. And from the side, you get the information from the same layer at the previous step. So this recurrent connection here is what will allow us to get a very good representation of these temporal sequences. You get present information and you get past information as well. Turns out that if now we zoom into this neuron from the recurrent neural network, it turns out that it's quite difficult to train recurrent neural networks because very quickly you get the problem of the vanishing gradients. So basically your gradients go very close to zero, and then of course then there is no possibility to train anymore. And one quite popular solution to the vanishing gradients problem is what is called the LSTM network, long short-term memory network, which is very famous. Very famous because it is widely used in speech recognition, in text, the autocomplete features of your phone use LSTM networks. So if you're getting the wrong word when you're writing a text, then you need to train your network more, right? It's not getting the work that you're thinking. So it is all based on the training data and on how the temporal dependencies of that data are being constructed. So the autocomplete is trying to predict what is the next word that you're going to write. And without going too much into details, if you're interested, we can discuss it a bit more later. This LSTM network has a quite sophisticated gating mechanism. What does that mean? What it means is that through these gates, for get gate, input gate, output gate, it tries to understand how important is the past information and how important is the present information. So through this sequence that you see here, it is giving a certain weight to the old information and it's giving a certain weight to the information that comes for this current step. And by doing that, it can learn the temporal or exploit, to put it in a better way, it can exploit the temporal dependencies in the data, and it can learn from those temporal dependencies how the data is structured in time. And then in the end, we're also training weights and biases. So you can see that you have different weights and biases in different in all these different gates. But what we are doing is just a very similar thing in the end, just that we are organizing the data in time. So the network knows, okay, I have a lot of inputs, but this one comes after this one, and then this is the other input from the next step. So then it can really understand how the data is organized in time, basically. And what we do is that we do first of all, an exploration of the architecture of this network. So we change the number of layers, we change also the number of, the length of the sequences that we are predicting. Here I'm showing the results, and I'm gonna walk you through how it performs. But in the end, the idea is that with a much smaller input, so here we only use 10 previous steps, we can get very good results. So remember that before we needed 500 steps to make one prediction, and now we only need 10 steps. Because of course, by knowing how the data is organized in time, then you don't need so much input information to get a good prediction, essentially. So if we now compare this LSTM1 architecture, it has only one hidden layer. And what I'm showing here is how much training data I use. So if I compare the results with 1,000 training data sets, that's the same that I had for the NLP, then we can see that we can reduce the error in the fluctuations of 20% down to 3%. So we can really improve significantly. And if we increase the amount of training data from 1,000 to 10,000, then we can further reduce the errors. So we can actually get errors in the mean of 0.5% and errors in the fluctuations of 2.5%, which is actually quite good. By adding a second hidden layer, we can further improve the predictions Here, with only training 100 with 100 data sets, we can significantly improve from the first row. So we can really, if we use more training data, we will get even better predictions here. What we also observe is that if we use too long networks for the input, so if we go up to 25, then the errors increase. And here we didn't explore this in very much detail. What we have observed in a bit of more careful studies is that there is a balance between how much the network is trying to learn the short-term predictions, so the instantaneous predictions, and the statistical behavior. So it comes to a point where the network may be trying to fit very well the instantaneous behavior of the flow, but then it may be missing the longer-term dynamics, and then the statistics can get a bit worse. So that's ongoing research, and there's some work here by Chiappa and others, basically defining a loss function that accounts for both, not only the instantaneous predictions, but also the statistical behavior of the flow. And here I'm showing the results of our best performing LSTM. So we get excellent agreement in the mean flow, the Streamwise velocity fluctuations, there are no shear stress, and instantaneous velocity fields look very good as well. Very good agreement with the reference. Interestingly, if we go to even more complicated statistics, we also see that the higher order terms, the skewness and the flatness, they're in excellent agreement, and also the vorticity fluctuations are very well predicted. So we can predict extremely well the turbulence statistics of this temporally evolving system. And again, this is not canonical turbulence. This is just a low order model of the near world cycle, but the temporal dynamics is in principle quite well represented. Something that I want to highlight, talking about the temporal dynamics, is how the instantaneous predictions are being carried out. Because we saw that the statistics are in very good agreement. If we look at the temporal evolution of the 9 coefficients, so here in blue you have the reference and in red you have the LSTM, you see that they are not on top of each other. Although the LSTM network is reproducing some of the dynamic events that you see in the reference, some of these bursts, some of these regions of high fluctuation in the higher order coefficients, but they are not on top of each other. In fact, you get 13% error in the predictions of the instantaneous coefficients. So this is because this model, this near world model, is a chaotic system. And of course, the network is predicting very well the flow, but it's not exact. It has a small error, and that small error is sufficient to shift the prediction to another trajectory, and therefore you're not having the same prediction. On the other hand, and I'll talk a bit more about dynamics in a second, we are currently developing some work in the context of the Koopman operator to improve the short-term predictions. So there are ways of keeping that short-term prediction better for longer, but of course any small error that you have will eventually push you to another trajectory. However, it is possible to try to understand a bit more the dynamics by looking at, for example, at the Poincaré map. So here what I'm showing is the portrait of the first and the third coefficients subjected to the condition of the hyperplane A2 equal to 0. And what we see is that the correlation between these two coefficients, which is basically the base laminar profile and the Streamwise vortices, it's in excellent agreement between the reference and the LSTM. So the dynamics of these two modes, they're very well represented. Even if instantaneously they can deviate to a different trajectory, the correlation between both two modes is learned properly by the network. And another indicator of the dynamics can be observed if one perturbs the reference data set. If one perturbs the reference data set, one is going to go to another trajectory, and that's what we see here in the vertical axis, and measuring the deviation between the two trajectories as a function of time. Here is the instant where I introduce the perturbation, and what you can see is that there is a period of exponential increase of that separation between trajectories, and eventually it settles at a certain level. And the exponent of this growth that you see here, that's what is called the Lyapunov exponent, and then one can compare those. So if one perturbs the reference system, one can get a Lyapunov exponent. If one looks at the perturbations within the LSTM predictions, one can get a different Lyapunov exponent. And what we see is that they are in excellent agreement. In other words, the deviations with respect to the reference series predicted by the LSTM are basically the deviations that you would have in the reference anyway, if you had such a small perturbation. So we can say that the dynamics are very well learned by the LSTM network, and that the instantaneous discrepancies, they come from the chaotic nature of the original system. But LSTM networks are a valid possibility and a quite robust possibility to predict the temporal dynamics of these, in principle, simplified, although quite realistic, turbulent flows, basically. So this is everything about the first half, everything that had to do with the temporal predictions. We have seen that it is possible to really get good predictions of the temporal dynamics through recurrent neural networks. And the second part has to do with the spatial predictions. So what we're going to do is that now we're going to get a turbulent flow, not a model, but a turbulent flow. We're going to measure in one region of the flow, and we're going to try to predict the flow in a different region of the domain. To do that, we're going to use what is called convolutional neural networks. Let me explain you a little bit more why this is a good choice to use this type of network. This type of problem of measuring at the wall, for example, and predicting the flow farther away from it, has been investigated before by Suzuki and Hasegawa and by Encinar and others, through linear methods, basically linear stochastic estimation. So you establish a linear relationship between the quantity measured at the wall and the quantity that we want to predict, essentially. More recently, we have a paper in JFM, here Sasaki and others, where we looked at transfer functions, so basically convolutions, where we consider both linear and non-linear transfer functions, and we saw that the non-linear ones perform better. So what you see here is the Streamwise velocity fluctuations at y plus 15 in a turbulent boundary layer. And here is the linear prediction. So you can see that the linear prediction, well, attenuates the fluctuations in some places. In some regions, it overestimates the fluctuations. So clearly there is something that is missing if you just do only a linear prediction. And as we know, scale interactions in turbulence have a linear component, which has to do with the superposition of the larger scales on the flow closer to the wall. But there is also a nonlinear component, which is the modulation. And if you have a linear prediction method, then you're going to miss all the nonlinear interactions. So in principle, it is reasonable to think that a nonlinear method will perform better. And as I mentioned in the first part of the seminar, neural networks are able to introduce nonlinearity in the predictions through this activation function. So we can perform, given that we have enough training data, we can perform nonlinear predictions by using neural networks. And we're going to consider this example. It's going to be a turbulent open channel flow. The reason why we chose an open channel is because in a full channel, you have interactions of the larger scales from one wall on another, as shown by Lozano Duran and Jimenez, and we want to simplify the dynamics a little bit. So if we only have one wall and then a symmetry condition on the top, then in principle, we don't have that interaction between walls. So that's a little bit simpler for our network to learn. We consider the Fourier-Chebyshev code Simpson developed at KTH to perform DNS, direct numerical simulation. Here, I'm going to start with a friction Reynolds number of 180, but later I will show you results at 550, and I will also show you results in a bigger domain. This is the first assessment. And all the details of this are in this proceedings paper by Guastoni and other. So this was developed in the summer workshop in Madrid by Jimenez. And then it was later developed a bit more to include more cases. So all the details are in this conference proceeding over here. So first, let me briefly explain why we think that convolutional networks are suitable for this problem. The first half of the seminar was based on fully connected layers, so networks with fully connected layers, which means that each neuron in one layer has a connection with all the neurons in the next one, and it's easy to see that that gives us a lot of parameters to train, right? I mean, all of these connections have a weight and a bias term, and images well, images are pixels, right? That's a lot. If you start to have high resolution images, you have a lot of data. And if you start to have many layers, then the amount of parameters increases exponentially. So that's not feasible. Fully connected networks for computer vision are usually not a good idea, at least fully connected layers all the way. Some connected layers can help at the end, but in principle, having all the layers fully connected will be problematic if we consider computer vision products. On the other hand, there is a tool that has received quite some attention recently, which is the use of convolutional layers. So these convolutional layers are based on what is called a kernel. This is this 2D window that can be 3 by 3 or 5 by 5. And this little window is sweeping through the image. And then, as I will explain later, all the information from this window results in one data point in the output. And of course, as you can imagine, this produces significantly fewer parameters than a fully connected layer. And at the same time, it's a quite suitable tool for analyzing the structures of images. So convolutional networks are extremely popular in computer vision because they are cheaper to train, they're easier to train, but they actually perform better. And I'm going to understand a little bit what these convolutions are doing. I'm going to discuss very briefly something that is probably basic for most of you, but just to quickly look at it. And it's convolutions in image processing. So essentially, how does this work? What is this convolution operation? And if you have an original, a starting image, F, which is a set of pixels, this is a black and white image, so it has only one input channel. And one defines a convolution filter, or well, in this case, I'm going to call it kernel first, because the 2D function is a kernel. When we get more kernels stacked on top of each other, then we'll get a filter. And the result of the convolution will be what is called the filter image. The convolution operation is defined here, which in practice, just very simply, I mean, it's equivalent to flipping the order of the first and the third columns, flipping the order of the first and the third rows, and then do the element by element multiplication, essentially. So this is the way in which you would get the entry 2 by 2, basically, 2, 2. So the result of the convolution operation is that at the end, you get one data point that has received information from 9 data points, essentially. And there are different filter kernels. So this is the easiest kernel. This is the identity. So clearly having a 1 at the middle and then zeros, it will not change anything. And the result of filtering this operation with a filter kernel, well, unsurprisingly gives me the same image as at the beginning. But there are more fun filters. It's not only about the identity. You can get what is called the box blur, which is this kernel over here. And the result of performing this filter operation on the original image is an image that is blurry, right? So we have managed to distort a little bit the edges and to create a bit of a more, of a lower resolution version of the original one. Another example of convolution in image processing would be what is called the edge detection. So edge detection is this kernel over here, and what you can see in the filter image on the right is that all the edges of the image have been highlighted. And this starts to become interesting because when we apply this to fields of turbulent flows, there will be features in those images. They will be treated as images, and those features in those images are what are going to be captured by the filter operations. So it could be that the convolutional network is picking up edges, is picking up blobs of high fluctuation, it's going to pick up streaky structures, clearly things that are found in turbulent flows. So those spatial features that would be identified in images is exactly what we are being able to pick up when looking at the fields in turbulence, basically. So just one more note, we have considered so far black and white images, which is basically one input channel. But if you want to have a color image, that means that you have 3 input channels, the red, the green, and the blue, which each of them is black and white as well, because it's only one individual channel that is varying. The combination of the 3 of them gives you the original image. So you can see how the reds are more intense in this red channel. And if one applies the 2D kernel on 3D input channels, then one obtains what is called a filter. and a filter of 3 times 5 times 5 would be applied to this input channel as follows. I will apply the first kernel to the first filter, to the first input file, the second one to the second channel, the third one to the third channel, and then I would add everything up at the end. So it is very easy to apply filters when you have multiple input channels. And the reason why I'm doing that is that when I go to Turbulence, it will be interesting to have several input channels, not only one piece of information to predict, but more than one piece of information. Now, enough about images. Let's go back to Turbulence. What are we trying to do? What we are trying to do is using quantities measured at the wall, in this case, the streamwise and spanwise wall shear stress components. So we have 2 input channels. We're going to predict farther from the wall the streamwise velocity fluctuations at the same instant. So we're going to use information from the wall to predict information far away from the wall. And because we have 2 input channels, we have to account for this procedure that I just explained when you have multiple input channels. This, again, all the information about this network and how everything is designed is described in these proceedings. So you can get all the information there. But this is the schematic representation of our convolutional network. So this is a network made up of different convolution operations. And we start here on the left with the input layer that has a depth of 2. I'm using 2 wall shear stress components, so that's 2 channels. And the output here on the right has a depth of 1, because I'm predicting only one field, the streamwise velocity fluctuation field. And what we have here in the middle is what is called the convolutional layers. I'm considering as an activation function the ReLU, the rectified linear unit, which is a very simple activation function, but it's very powerful in computer vision. And I'm having an input of 128 square points, which is the resolution of that plane that I'm considering. Okay, so how does this work? Well, in practice, what I do is that I have in my first layer a filter of size 2 times 5 times 5. Okay, so the 2D window would be 5 by 5, meaning that we have 25 points to produce the output of 1 point, and that gives me only 50 parameters. To give you some perspective, if I would do this with a fully connected network, then I would need 128 squared times 2, so more than 32,000 parameters. So you can really see that there is a huge decrease in the amount of parameters, and you can see why this is helpful for computer vision. And actually, when I apply this filter, then what I do is that I apply this filter a total of 64 times. So I stack all the feature maps here, and I get 64 planes with features. What is a feature? Well, a feature can be an edge, can be a certain characteristic of the image that has been picked up by the filter. And what is interesting is that when I start to go deeper into the network, those features will be combined into larger things. So the first layers look at local information, look at very small things, but of course, when you start to go deeper into the network, the outputs are going to be receiving information from more and more points. So they are building up towards larger structures as you go deeper into the network. And this is actually something quite cool, because if you think about it, there is a hierarchical distribution of those features, which is something that we observe in Turbulence all the time, that hierarchical basically setup of the scales that are being identified. So this is why convolutional networks are helpful in image processing and computer vision. This is because we are able to really exploit the hierarchical structure of the data with much fewer parameters. And this is what I was mentioning at the beginning. You can have at the end a fully connected layer, so you get a global output, for example, to tell you that this is a car, but you can also have fully connected layers all the way. This is going to be our case, which means that at the end, I don't get one single output, meaning this is a car or this is a cat. What I have is a field where I'm identifying what is a car, what is a cat, what is the road, and so on. So this is obtained when we have fully convolutional layers all the way. And this is the approach that we're going to take here, because we want our output to be another field, like the input. So some results, I will maybe not spend too much time so that we can have some discussion at the end. But here what I'm comparing is the Streamwise velocity fluctuations predicted at y plus 15, so in the region of the near wall peak. At the center, I have the reference, which clearly allows us to see the near wall streaks. On the bottom, the neural network, which provides excellent predictions of this field. And the LSE, the linear stochastic estimation, starts to exhibit a certain attenuation of those fluctuations. So because it only accounts for linear interactions, the predictions are not as good as what one can do with the neural network. This becomes even more prominent at y plus 30, where the LSE really filters the output quite significantly. And at y plus 50, the LSE is quite blurry, and the network retains some of the structure in the data, but the predictions are not as good, of course, because the data is less correlated. One way to improve the results of the network far from the wall is to increase the time step between samples. Because of course, if you're farther away from the wall, then the scales are much slower, therefore the samples are much more correlated, so you're not getting so much data from your samples. So when we are going farther away from the wall, we can increase the time step between samples, so we are effectively having more information, and you can see that the validation loss is lower, and the field is in better agreement with a reference. So if we look now at the turbulence statistics, here in these orange triangles, I'm showing the mean flow and the Streamwise velocity fluctuations. We can see that close to the wall, the agreement is excellent. And as we move farther from the wall, then we start to have higher deviations with respect to the data. If we increase the time step between samples, we don't see a difference close to the wall, but far away from the wall, we improve because we basically have less correlated samples, which means that we have more information to basically train our network. And the LSE, the linear stochastic estimation, the linear prediction, that one is the worst. So clearly, because we only capture linear interactions between the input and the output, we're having a worse estimation. So if we look at the percentage errors, the near wall peak, we can get less than 3% error with the network and 12% error with the LSE. Farther from the wall, we get 30% error with the network. And this is something that we have been able to improve a bit more in our more recent study. So let me dive into it. We have now extended this work to a friction Reynolds number of 550. So we have increased the amount of inputs. Now we also consider the pressure. So we consider the two wall shear stress components and the pressure as inputs, and the output is the three velocity fluctuations. So not only the streamwise, but the three velocity fluctuations. So we scale them so they are in the same range, and we also apply periodic padding to the input, so we can basically exploit the periodicity in the underlying data that we're using for training. And by the way, all of this is also available in a recent preprint. So this is by Guastonia and others, and all the details of how we do all the setups are also discussed in this preprint. So also feel free to discuss if you're interested in that. In this work, we introduce another approach, which is also discussed in this work in physics of fluids by Güemes and others, which is basically to not predict just the flow, but we perform a POD, a proper orthogonal decomposition, and then we predict the temporal coefficients of the POD modes. Why do we do that? Because by doing so, we encode some of the physical behavior of the flow through the POD modes, and then we only need to predict the temporal dynamics. So this is a bit similar to what we did at the beginning with the Moehlis model. And here you see how we do it. We take the domain, we decompose it into smaller subdomains, and we perform the POD in each of these squares. The reason to do that is that all the scales larger than the domain size get lumped into the first POD mode. And of course, that means that with fewer modes, we can actually reconstruct the signal. So it is less work for our network to predict, because we only need to predict fewer mode coefficients, essentially. And this is how the data is organized when performing these predictions based on POD modes. So this is a comparison of the results. What we have, and this is all at eta of 550. What we have on the third row is the reference DNS. On the bottom row here, and the first column is y plus 15. The second column is y plus 100. What we see is that the FCN, the fully convolutional network, so basically the approach based on predicting the full field, is in excellent agreement with the data, as before. It gets worse when one compares with the flow farther away. And what we can see is that the convolutional network with POD actually performs better when we are farther away from the wall. Why is that? Well, it kind of makes sense because close to the wall, it is quite easy for the fully convolutional network to just reproduce the full signal. But when you go farther away from it, it is in a way more useful for producing training data to just encapsulate all the spatial distributions into the POD modes and just train to learn the temporal dynamics. So the message is close to the wall, the network that reproduces the whole field performs better. Far away from the wall, the network that predicts just the temporal coefficients of the POD modes performs better. And here, as a reference, I'm showing a linear prediction, in this case through extended POD, but that's formally equivalent to linear stochastic estimation, and the results are as before. So basically, we get an attenuation of the fluctuations when we only consider a linear prediction of the flow. And here I'm showing the predictions of the streamwise velocity fluctuations, as well as the one normal and the spanwise. The triangles are the convolutional network, so basically predicting the full signal. The blue circles are the predictions through convolutional network of the POD modes, and the green squares are the linear prediction. So what we can see is actually consistent with what we saw before. So the extended POD, the linear method, performs worse. Far away from the wall, all the methods start to exhibit discrepancies. And what we see here is that in the case that is farthest from the wall, the network based on POD is a bit better than the one based on the fully convolutional network, basically. And you can see here the error levels. We actually get quite good predictions. I mean, close to the near wall peak, we make less than 1% error in its prediction, so it's essentially very well predicted. Far away from the wall, at y plus 100, we actually get only 26% error in the streamwise velocity fluctuations, which is a quite good accomplishment, keeping in mind that we're very far away from the wall. And then just to conclude, I would like to briefly mention a couple of examples of something that is very trendy in machine learning, which is transfer learning. And transfer learning, I think that there is quite some potential in this approach. It's basically the idea of transferring the knowledge learned by one network to another one. So we don't have to redo the training all again. And of course, in the context of efficiency and code development in a practical way, this is very practical. So if we first look at the 180 case, what I'm showing is that it is possible to freeze the 3 first layers from the network trained to predict at y plus 15. And if we want to use this same network to predict at y plus 50, so farther away, I only train the 3 last layers. So basically, I freeze the first layers, the ones that are looking at smaller features, and then layers that are later on, the ones that look at larger features, those ones are left free. And of course, that kind of makes sense because I would expect the smaller scales to be more or less similar at 15 and 50 plus units, and of course the larger scales to be different. So I can exploit what I learned at y plus 15, and I don't need to learn it again for y plus 50. And the results show that we get very similar results in terms of mean flow and fluctuations, and we save more than a factor of 3 in terms of training time, in terms of computer time. So actually, this really helps me to transfer the knowledge and train more efficiently the network at y plus 50. And this, I would say, that is maybe the most remarkable result, and is that we are able to transfer the knowledge learned at 180 to 550. Which this is, of course, only one example of how to do this transfer learning. There are many applications, and we're looking at some of them right now, of how this can be done, but it's actually something quite promising. What we do is that we start training the 550 case from the weights that we got at 180. So we don't start from a random initialization of the weights, we start from the weights that were obtained at 180. And what we see here, this is the validation and test loss as a function of the batches, of the training batches. In orange, I showed you the results where I trained the 550 starting from random weights, so the usual procedure. In gray, I'm showing you the validation loss and the test loss when I start from the weights at 180. So I don't start from random weights, I start from the weights that I learned at 180. And I can see that the error is similar, slightly lower, but similar. But what is actually quite interesting is that if I start from the weights at 180 and I use only 50% or even 25% of the training data, I obtain essentially very similar error levels. In other words, by transferring the knowledge that I had at 180 to 550, I only need 1/4 of the training data to get very similar results. That you can also see here in this table where I show you the statistical errors in all the fluctuations. And this, of course, is extremely valuable because producing the data is costly. I mean, this is doing a DNS at 550, but if we extrapolate that to a much higher Reynolds number, then one can really see the benefits. And this doesn't only apply to the training. I mean, we can also explore possibilities where we can transfer certain features that are learned at one cheaper case to cases that are less easy to obtain. So if one starts to look at DNSs at 2,000, 5,000, which are extremely costly, it could be that we can make predictions of many quantities learned at a much, much lower Reynolds number and therefore a much cheaper case computationally. And then this is a slide where I have some wish lists or where some future directions we want to look at different possible areas where machine learning can help. Of course, generation of inflow conditions and boundary conditions, which have been looked at, SGS modeling, structure interaction, flow control. By the way, all the stuff that I have discussed today about non-intrusive sensing has its motivation in flow control. So I want to be able to measure at the wall, which is much less disruptive than measuring in the flow. And then if I can get a very good idea of what's happening far from the wall, then I can have a much more efficient control. So this for reactive control can be a quite powerful tool to have this non-intrusive sensing. And then an area which has received some attention recently in the group of Koji Fukadata, that's the use of autoencoders for model reduction. So I really think that this type of application will really see a lot of potential in the coming years. Basically to perform nonlinear model decompositions through autoencoders, which are really showing quite some interesting applications. And with that, I would like to, well, this is a summary of my conclusions and my results, some areas for improvement. I would like to thank you very much for your attention, and we have some minutes left for taking your questions. Thank you.
Thank you very much. And on behalf of everybody, hopefully everyone's clapping. So
some virtual claps from Julio.
Yes. It's very easy to confuse the virtual claps of people raising their hand. I now invite people to ask questions. You can either do so by clicking on the participants button on the bottom and raising your hand, and then I'll see it. Or alternatively, you can type something into the chat question and then we'll let you ask something.
I have a question, if I may.
Yeah, go ahead, Professor Brown.
Yeah, so Richard Brown from QUT.
Hi.
Hi there. Yeah, look, thanks. A great presentation, very sort of high level and low level content, and very clear. So thank you. Look, I'm just wondering if you could make a comment about the relationship between this work and STIV, space-time image velocimetry, which is not exactly this technique, but the concept of using some kind of image or series of images to look at surface velocities of flows, in particular environmental flows like rivers and estuaries.
Yes, I mean, I'm not familiar with all the details of STIV, but I really see that there is quite some similarity in using data-driven methods to exploit images. In particular, something that I for experimental approaches, I think that something that could really help quite a bit is to increase the time resolution between samples, for example. So if you have a set of PID snapshots, and then you have a certain limitation on the frequency that you can obtain those snapshots. But if you train from a simulation, for example, with an LSTM or some recurrent network-based approach, then you can maybe try to fill in the gaps between those snapshots through a data-driven method, if you have good training data. So something in that direction of using machine learning in general seems to help a lot in applications where we want to fill in the gaps. So if we have a simulation where we have all the information, we can train a network and then go to an experiment where we have gaps because we cannot measure everywhere. The machine learning seems to help in those applications. So yes, I believe that this will open many new areas where one can really exploit these data-driven approaches. Absolutely.
Thanks for that. Just one supplementary question. In environmental flows, there's the issue of comparing the accuracy of the measurements, which are video images, with that of a model, which is primarily what you've used, and it's orders of magnitude higher. So I'm just wondering if you have any comment about the accuracy of the input data for the AI models in general.
Yes, I mean, of course, if one goes into environmental flows where one cannot have such detailed simulations, then that's a completely different story. Absolutely. I mean, this is a DNS, so of course it's a fully resolved simulation, which means that if you would do an experiment of this same case, they would be in very good agreement because we're using actually very high resolution DNS for these AI models. So I would imagine that the input data used for these neural networks is of very high quality, and it would be in very good agreement of a similar experiment. But if one goes into cases where one cannot have such a high quality simulation, and if one goes into environmental flows and one needs to start to model and then have also a wall boundary condition that introduces much more uncertainty, then the more model assumptions in your data, well, the more problematic it is then to train a good data-driven model. So it all boils down to, well, not all, but a big part of it boils down to how good your input data is. So for this case, because it's a very easy case, it's a channel, then the input data is very good. In more complicated cases, then one needs to start to think. There are hybrid approaches, experimental and numerical ones. So there is a lot to explore there.
Okay, great. Thanks very much.
Thank you for the question.
Professor Theophilus, I think you're next to go.
Thanks. Ricardo, great talk. Thanks very much. Introduces quite a few concepts that are working. If you go to page 30, please, of your slides, I saw something that was reminiscent of transition, which is where I want to take you. So this reminds me, I mean, conceptually, of a very nice prediction of linear behavior, which is a simple thing to do. The trouble is that some of us would argue that transition is much more difficult than turbulence, in the sense that as this principal linear mode grows, other modes will come up non-linearly, and the non-linearity, which modes and how strong they are, will depend on the initial amplitude of the linear mode that grows. So can you please comment on the interplay between determinism that we need from the Navier-Stokes operator and this powerful prediction method in order to make some progress there, other than doing n DNSs for each of those scenarios?
Yes, I mean, you brought up several interesting points. First, of course, here, I mean, this is fully turbulent. So here I'm not looking at the transition, but of course, as you point out very well, we're looking only at the leading Lyapunov exponent. We haven't looked at the Lyapunov spectrum, which would give you additional details of the dynamics that we have not compared. So of course, there is some more things to do there. And this is only about turbulence. If one goes into transition, well, that's a whole new world also. And that's why on purpose we excluded time series that were relaminarizing. or that were in kind of like intermittent states. We only focus on the simpler problem of turbulence. I have, however, a feeling that by exploiting some of the, what I have observed in my experience of looking at these data-driven methods is that if you know something from the physics, you should use it in your model. You should not allow your model or use computer time to let your model learn something that you know from physics. So as you also point out very well, things that we know from the Navier-Stokes operator, we should embed it in our model. So if the flow is incompressible, then you should impose the incompressibility, maybe going to a latent space through an autoencoder where we impose the incompressibility. If the flow is periodic, then you should allow your network to exploit that periodicity instead of forcing it to learn it. So yeah, it's a bit hard to see what new directions in the context of transition would help, but certainly exploiting the things that we know from the physics, that should be added to the networks. We don't have to learn what we know from the physics.
Teach everything. Thank you. That probably leads to my other very simple question. From looking at textbooks and easy stuff, you see some discussion of single layer networks, but of course you work with multiple layer. Can you please explain, does that touch upon what you just said? The teaching of...
Yes, so there is one, when you add one hidden layer, so you basically have two output layers, so one output and one header, not single output networks, but more than one output network, then you start to significantly expand the predictability capabilities of these neural networks. And that was something that, when already in the 70s and in the 80s, they were doing a lot of work with single output networks, which at some point they became limited. They were trying to have very long, many neurons in that layer. And at some point they were hitting a limitation in the prediction capabilities. And with higher computer power and more diverse data sets, then it came to the realization that having one extra layer, it significantly expanded the possibility of predicting. So if you have the possibility of adding parameters to your network, it is usually quite helpful to add more layers than to have one single output layer. So basically, yes, it helps to have multiple output layers. And to connect with the physics, in the end, if you have only one output layer and you remove the activation function, so you remove the nonlinearity, then you just have POD. I mean, that's what Milanos and Kumosakos showed in 2002 in their early paper. They did a very, very nice comparison. They started with POD, then they introduced neural networks. They really showed how the neural network gives you the same as the POD if you just remove the nonlinearity, because it's the same. And then they just showed quite nicely what is the performance improvement. So it really goes in that direction. What we know from the physics should be embedded in the model that you use.
As a hidden layer.
Yeah, so the hidden layer, having more than one layer, it really helps a lot in the performance.
Thank you.
And then maybe what you're also referring to is is the use of autoencoders. So in these autoencoders, you first reduce the dimensionality of the problem into a space with a certain property, and that is where you can maybe put the incompressibility or any other physical constraints that you know.
Thank you.
Thank you.
Anybody else have any questions? In the meantime, I actually have a question. Ricardo, you mentioned something about the Koopman operator, and when you were talking about the first neural network, the MLP one, I immediately kind of thought of Koopman operator, where I guess your input states are not necessarily linear things, but they can be nonlinear things. So things like U squared, blah, 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 blah.
Yes.
I'm wondering if you can maybe give a high-level overview of how you see the Koopman operator coming into play for some of these problems.
This is work, you can see all the details in this preprint. That's work done by Hendresa Ibasi in collaboration with us. The idea is that, so through the Koopman operator, then you essentially have linear predictions, but it is possible, that was also shown by some work by Branton and Kutz, to embed nonlinearities as a forcing. So then one can add a forcing to the system, which includes nonlinear interactions. And what we show in this work is that if you introduce second order nonlinearities, those are the same as the one in the Moehlis model, then you can reconstruct the data pretty well and improve significantly the short-term predictions, because it encapsulates the physical behavior that you have in the original model. But more interestingly, if you have even higher order nonlinearities, so the reference model has second order, but we introduce second, third, and fourth order, then the model picks directly the correct ones. It gives 0 coefficients to the higher order nonlinearities and goes directly to the correct ones. So in a way, knowing the underlying physical behavior, and then, in this case, introducing the nonlinearity through a forcing, it can really help in the predictions a lot. This is, of course, under investigation, and we're trying to learn more, but this type of approaches can also help very much.
Great, thank you. I just want to say I really like the fact that we could see during this talk some of the machinery and some of these neural networks. I feel like most, in the interest of time, I guess a lot of talks skip over it, so it's helpful to see some of the actual machinery behind the predictions, so thank you for that. Anybody else have any questions? If not, let's thank the speaker again. Thank you very much, Ricardo, for giving this talk for us. It was very, very good for the Melbourne group since it specializes in turbulence. And thank you, everybody, and we'll see you next week.
Thank you very much.
Thank you, Ricardo.
Thank you. Bye-bye.